Okay, everyone. So for the first talk of the afternoon, we have Deeparnab who will be telling us about round of cut technique for clustering.
Thank you, Basil. Thank you for the organizers for inviting me. It's great to be in San Diego, away from New Hampshire in this time of year. Although October it flips. Let me begin with three apologies. So one is my voice. It's handle the mic there. Second is, I think many of you have given this talk before, and many of you in the audience have seen this before. So I have to rely on the fact that my last, unfortunate truth, the last talk was not memorable. So and the third is it's actually a technical talk. It's about technique. It's only technical, and I understand 60 minutes of technical things. So please ask questions. In a previous version, I had jokes, but this time I don't even have that. So with that, what is this going to talk about? It's going to be less about, well, it's going to be about clustering, but it's a more general technique in design of approximation algorithms. And I want to sort of, it's been around for a while. So in any discrete optimization problem, you write an integer programming formulation, and then usually you start looking at its natural NP axis. So you take out the integer constraints, and the integer op, let's call it opt, LP of is LP. And so rounding algorithm will take the solution to this LP relaxation and try to get an integer solution. And you get an alpha approximation. The cost of the rounding algorithm solution is at most alpha times the LP that's shown, and which implies an alpha approximation equals to opt. And the best approximation factor you can hope for using this is called this integrality gap, which looks at the worst instance, the gap between the LP and the opt. So it should be the other way around because opt is larger than it. Okay, so this is just sort of a primer. So once you get a LP relaxation which has a bad integrality gap, how does one move forward? Well, one can add valid inequality, strengthens the LP, and it basically says instead of looking at P, I'm looking at something which is smaller than P, the set Q, and I want to minimize C over Q, and I'll get something which is better. It's a stronger LP relaxation. And there are many generic ways of doing it. Maybe so. One is via these hierarchies. So you sort of add Adams hierarchy, other kinds of hierarchies to achieve stronger and stronger LP relaxations in a systematic way. There are other problem-specific ways of doing it. So you take a problem at hand and you say, okay, these valid inequalities can be added, and sometimes you add exponentially many valid inequalities, and you can separate them. Then using that ellipsoid algorithm, you can solve the LPs. So there are various ways. What I want to highlight in this talk, one of the things is there is this approach of round or cut, which sort of falls more in the second. And it goes a little bit like this. So it uses the fact that the ellipsoid algorithm is at its heart. So I want to solve this problem. So let's begin by saying I want to check if opt is a guess of the value, and I want to see if this polytope here is empty or not. Okay. So if the smallest of four this is non-empty, I will have some. I'll have a good approximation. And it begins as follows. So I start off with any point, right? And I try to round it. So there's a rounding algorithm that will be needed, and I'll try to round this LP solution to get a good fractional point. So what a good fractional point means, its cost is not too much bigger than my guess. So it's at most alpha times opt. And if that is the case, then I have an alpha approximation with respect to this good guess of opt, and I'm happy. But if that is not the case, if I fail, then what I would like to do is I'd like to say that this point X was actually a cheating point. It should not have been in my photo. So I want to cut it away from the thing that I'm trying to optimize over, set Q. And oftentimes this cutting away, so round or cut paradigm is not, it's not for any point Z that I'll be able to cut the thing away. It would be rather the fact that I failed to round. I want to use that to cut the point. And that's all that I need. So it's good to contrast the previous thing. It says I have a separation oracle, means any point I can either say it's in the polytope or I can cut it away from my polytope. But I don't need that. Round or cut basically I don't need that strength. I only need it for the case when my rounding algorithm fails. And if I can indeed do this, then I say feed this separating hyperplane to ellipsoid algorithm, ellipsoid algorithm will give me a new x, and I keep going on and on like that. And the power of the ellipsoid algorithm is that in polynomially many rounds, either it leads to happy state, we get an alpha approximation, or I'll prove that this is empty, in which case I will take negatives. So that's round robin. So what is this talk about? So I want to sort of highlight the use of this paradigm for some class of clustering algorithms that are going to come up. But I thought it's a half the whole hour to start a little bit of the first work that began this round of paradigm approximation. So this is again a work that is well known to many in this audience. It was a paper by Carr, Fleischer, Leung, and Phillips from 2000, so that 2000. And it had many things, but it sort of used the toy example, which I think illustrates the power of this method. It's a very toy example. It's a minimum knapsack problem. So the problem actually has but let's use it to get it to approximation. So let's begin with this LP relaxation, natural LP relaxation. Okay, so what is the problem? I have a bunch of items. Items are profits and costs. There is a parameter K. And unlike the knapsack problem, I actually want to pick a subset of these elements which gives me at least K amount of profit. I want to minimize it. So it's a minimum knapsack. So I write this natural LP relaxation. And this has a bad integrality. So if I have two items, even like the first one's profit is K minus 1 and the second one's profit is 1. So the cost of the first item is 0 and the cost of the second item is 1. So what is opt of this? So I have to take both the items, so opt is 1. But what is LP? So LP can cheat. It basically says, let me pick the first item fully, and then I have only one amount of thing left. So I'll take 1 by K amount of that item, second item, and LP will be 1 by K. So integrality gets K and K. Yeah.
So profit of the second guy should be K. Yeah. Or maybe we need to flip things around a little bit. Something things a little bit. Because right now, if you want profit K, then you need both the items. I think maybe flip it around.
You want profit K, you need to say both x1 and x2 equals 1.
Did I mark up something? So P2 should be K, you say. P2 should be K.
P2 should be K.
Or K, or even K minus 1.
Whatever.
K
Yeah.
minus
But
1.
then P2K, then the opt doesn't change because opt just picks the second item.
Correct. P2 should be. Thank you very much. This was not deliberate. But it is important though, so I'm sorry to make this. So P2 should be large here. So this is a bad integrality gap example, but it can be easily fixed by adding a valid inequality. And this class of inequalities, this is one I want to sort of spend a little time on, is the following. So it says the following. So it says,
So somebody's asking what's the mistake.
yeah, so I think the mistake is that if P1 is 1, then the x1, x2 that I gave is not a correct solution, is that? Because P2 times x2 is still 1 by K, it does not get to 1. I hope that answers the question. So P2 should be large. P2 should be K minus 1 or K even, and then it will be all fine. Okay. Good. So what is the fix? Well, the fix is to look at this class of inequalities. These are called knapsack cover inequalities. And it says the following. So consider any subset of items S, okay, and imagine that I've already picked them. Okay. So if I've already picked them, then there is a residual demand of K minus PS left to be obtained from the remaining items. And so you just have this sort of, the left hand side has Pi tilde Xi over I not in S. And the only difference is that the Pi tilde has been brought down. Okay, so if I have some residual demand of only 1 unit left, and Pi is something very large, then I should actually be able to cover it even if the Pi were much smaller. In particular, I can cap it at the residual demand. So that was indeed that should have told me that P2 should have been high, but it's sloppy there. And if you do add this constraint for the set equal to the first element, then you notice that the residual demand, even if I take the first element, is still 1. And now if you have P2 tilde, which should be the minimum of P2 it should have been k, and 1 comes down to 1, I don't have 1 times x2 equal to 1 if x2 1. So it sort of acts as a hyperplane that separates out this wrong LP solution. Okay, however, there are exponentially many constraints. Now, these constraints are not very difficult to optimize over, but they cover knapsack itself, but you can get an FP task. So that's one way to attack the problem. But the other way, and this is what Carl Fisher and have in their paper, is they basically say, here's a schema of the same round-off cut method as follows. You start with any solution to this LP, which has, without the yellow constraint, the first two things. You use it to round it. And the rounding scheme is a decomposition scheme. They take this x and they use 2x to get r different solutions. These details are not important. They get r different solutions which decompose the elements, and if each of them gave profit at least k, then they'll be happy, they'll get a true approximation. And if not, if any one of them has less profit than k, then they use it as a candidate, one of these inequalities to separate this element x from this whole big LP. So they're not ever solving this big LP. They're only taking a solution and trying to see if it is, they're basically trying to use ellipsoid on this, but the separating hyperplane is generated on the fly, only on the rounding hyperplane. Okay, so again, this is not what I want to talk about. This is sort of trying to give a history of where this problem came out. However, any questions about the schema? The schema is basically generating a cuts on the fly. Now, this paper had a lot of follow-up work. And so these are usually, and especially for covering problems and also capacited covering problems. There's a whole set of works in scheduling, network design, allocation, and also in clustering. So in particular, it gave the first LP-based algorithm for capacited facility location. So capacited facility location is a problem. Again, I'll not go into the details, but I think Samir mentioned capacited K center, but it's the same thing. Every facility can cover at most some number of clients. There was an LP, there was a local search-based constant factor known, and it was an open question whether there is some LP-based algorithm known. And there was a paper by Levy, Schmoes, and Swami, who sort of said maybe these knapsack cover kind of inequalities can help. And indeed, paper by Arn, Singh, and Svensson did that. That's the first thing. So there are many other follow-up things. I think capacity K center, Shi has a bunch of works, which capacity K median, I'm sorry, where you get, if you violate the number of centers a little bit, or the capacity is a little bit, you can get constant factor approximations. So there has been a lot of works which uses this snapshot of this round-off cut method in approximate mathematics. However, I think almost all of them sort of work in the sense where the set of valid inequalities are upfront known. There's some sort of knapsack cover or generalized knapsack cover. There are exponentially many of them. And you know that all of them are valid, and you put them in, you cannot separate over them, but you try to find something on the fly to use it. So I think technically what I want to sort of stress going forward for clustering problems that I will talk about is that it was a priori not clear which valid inequalities to put up front. Rather, the valid inequalities itself will come from the rounding algorithm. So that's maybe at a technical level, which is something different from all these things. And I mentioned one paper in the end where the facility location or with Matroid or knapsack constraints, which has Krishnaswamy et al. And Borna is one of the co-authors. They actually have an example, I think, of a problem where the knapsack cover inequalities don't. So if you just add all the knapsack cover inequalities, even then there's a bad inequality. And they have to design some other kind of algorithms. Good. So with all that, I will stop talking about generic approximation algorithms. We will now focus on clustering problems. And Samir gave and I'll be talking about the K center objectives. So Samir's morning talk has already warmed you up what they are. We're also going to go over them, but it will be a little fast. But as usual, as if there is any question, please stop me. Anytime I get a chance to stop talking, it will be beneficial. Okay. So the setup is the same as I'll be talking about the supplier version. So I'm going to talk about clusters and centers and facility clients and facilities. They both live in a metric space D. What is the goal? The goal is to output or open centers S in the set of facilities. And once you open them, at least for the most of the top till I reach my open problem, once you open them, every client will go to the nearest open facility. And it will pay that distance. That's the distance that the client pays. So the case center problem, I'm still calling it case center, although it is case supplier. Now that's the asterisk there. Case center in this version, the constraint on the set S is that there should be at most K clients. And the weighted version of the knapsack center problem, every facility has a weight on it. And the constraint, instead of cardinality being at most K, would be the weight. That's the case center problem in the knapsack center. So that's the constraint. And the objective is I want to find a solution so that the maximum distance traveled by client is minimized. So those gives me those two problems. I think as Samir mentioned, these have good approximations. So I'll be focusing more on the outlier version, where again, this objective function is very sensitive to outliers. So if you have a point right at the bottom, suddenly the objective will blow up. So instead, one looks at the outlier version. So I'm going to cast it slightly differently from what Samir said. Instead of looking at outliers, I'm going to think of inliers. So along with that input, I also have a number M, which I should think of as a number of people I want to cover, inliers. So I want to not only figure out the set of centers S, which is a subset of F, I also want to figure out a set of clients T, which are at least M elements. And now the objective is only to minimize the maximum distance traveled by the inliers. I can throw away all the fellows who are not in T, who are my outliers. And I only care about my inliers, and I want to minimize the maximum distance. So K center has the objective S is at most K, knapsack center has objective, the weight of facilities open. So what we saw in the morning, so and I'll go over the algorithm again. There is an algorithm which gets 3 approximations for the K supplier, K center, K supplier problem. It is just tight. You cannot get anything better unless people are deep. And in fact, a very similar algorithm, I might mention, but the algorithm is also does the weighted. The knapsack center problem also 3 approximations. When I
Quick question,
yes.
so the shoe, Nemhauser, 79 neighborhood, do a hardness or they do both?
No, they do hardness, they don't have an algorithm.
Okay.
Very hard for dominating. Good. Now with outliers, as I think so we said in the morning that he had an algorithm with Charikar, Mount and Narasimhan, which is this greedy algorithm, a very, very nice, clever greedy algorithm, which I think it also works with the supplier version. It gives a 3 approximation. So even for supplier, we have 3 approximation. And as you mentioned, for that, the paper with Ravi Shankar and Prachi Goel, we actually got a 2 approximation. But actually, for the supplier version, not better than 3, so we also get a 3 approximation. So I'm actually going to spend a little time on the second one there, because the first one, somebody already talked about it. But the thing that was left open, so this is the third quadrant, whether for the knapsack center with outlier, something can be done. And as somebody mentioned, there were papers which violated the budget a little bit and got 3 approximation. But the true approximation was open. So those are sort of by criterion approximation. But what I want to spend time on is how this rounder cut method actually gets 3 approximation for this. And I think I don't know if any other way of getting this 3 approximation. So the rounder cut, of course, one of the con about that is it's going to be slow as it uses the ellipsoid. So I would like to know if one can get it faster or combinatorially established. This is, I think, as far as I was spoken. So that's going to be the agenda. I'm going to go over this. Okay, so the plan is to go over the Hopcroft-Moyes algorithm. So I'll cover the 3 approximation case center. and I think mentioned something about the knapsack. But then I want to spend some time on LP based tree approximation for outliers. That's with Goel and Krishnaswamy, and that will set us up for getting the round trip, I think. So that's the plan. Again, before I move on, this is the kind of thing that I think somebody also mentioned. We're going to assume that we know the optimal radius. So we're going to guess the optimal radius. And basically, the problem is going to be given an instance and an R, parameter R. Either I find a solution within distance at the cost at most 3R. So I have every point covered with at most 3R from an open center, or I should be able to prove that the guess is too small. So if I can do this, then I have a clean approximation. So I'm going to basically assume that I always know. Okay. So here's how the hog functional algorithm works, right? So I have centers, I have clients, I have facilities. Pick an arbitrary client. Again, I know the R. So this is an arbitrary client, and I put it in my representative set. I open a ball of radius R, and I pick a facility from there. Okay. And I pick it and I open it. And after opening it, I draw a ball of radius 2R, and any other client that is present in this ball, any other blue point is present in this ball, becomes a child of this representative. The representative is responsible for these points that have a ball of radius 2R. And I remove them from the client set and I repeat. So I remove them from the client set and I repeat this procedure if all the clients have been empty. Okay, so I pick a client, I draw a ball of radius R, pick a facility, draw a ball of radius 2R, remove clients, I keep doing this. I'll be complete. So, two things. Oh, I'm running the okay. So, first thing to observe is that every client is within 3R distance from some open set. Okay. That's simply because it's within 2R from its representative. The representative is within R from open facility. So in triangle inequality, I'm getting 2. What is less clear, if you've seen it for the first time, is that you actually open at most K centers. But the reason for this is if I don't open at most K centers, observation is that any two representatives are at least 2R distance away. So if I have to open K plus 1 facilities, and there are K plus 1 representatives which are pairwise distance at least 2R away. So not only my solution failed, any solution will fail. And that will basically prove that R is too small. So I'll be in case B. So I will just bump up R and repeat. So that's basically the problem. Good. So this leads to a tree approximation. Okay, a little word about what happens if I want to do the weighted, the knapsack problem. Nothing changes except when I, instead of opening an arbitrary facility here, I just open the cheapest facility. So every facility has a cost. So open the cheapest facility, and we can show that cost, that even if the cheapest facility crosses my budget K, then there cannot be any solution. So it's basically the same algorithm, except I just change which facility I am. But let me not go to knapsack center directly. Let me go to the fact where I have outliers, and let me give a different algorithm for this than the greedy algorithm that somebody talked about. Okay. So let's write what the LP is, right? So the LP is the following. I have a variable for every facility that I open it or not. And I have now a variable for every client, whether I'm going to be treating it as an inlier or not. So XF and curve B. And what are the constraints? Well, the first constraint says I open K centers. And the second one says that, the second constraint says I have to have at least M inliers, I have to cover at least M fellows. And the thing that connects both of them is the following. Basically says if I take a client V and if it is being covered, then I must open a facility within a ball of radius 1. So if I look at a ball of radius 1 and look at the total fractionally how many things that you opened, or radius R, fractionally how many facilities I have opened, that thing must dominate the value of tau. So that's what this thing. So basically, if I have to draw a ball of radius R around any client, the total X mass sitting in that ball must be at least tau. That's sort of picture take over. So that's an LP, that's a succinct LP. So if my guess is correct, then this LP is feasible, or contrapositively, if this is not feasible, my guess is wrong. So what I want to show now is that if my guess is, if this thing is feasible, I can actually cover every client within distance 3R. And the algorithm is basically the same algorithm as Hogwarts, except I'm going to use the LP values to guide how I open my facilities and clients. Because I'm also going to sort of mark the changes. So Hogwarts was pick arbitrary facility. Now I don't pick arbitrarily, I pick greedy. Pick an arbitrary client. Instead of that, I pick the client with the largest curve V. So I want to pick a representative which is covered. I don't want to pick an outlier to begin my search. Now I pick this V, I draw a ball of radius R, and earlier I pick an arbitrary facility and I open it. This time I will not open it. I will select it or tentatively open it. I'll keep it in my bag for later consideration. So I select an arbitrary facility. Then I draw a ball of radius 2R around that. All the clients that are in there become my children. I'm responsible for them. And I keep continuing. So I do that. So well, this I chose that. I selected that facility. I draw a ball of radius 2R. Then I do that. Same. And this fellow is far away. You know, it comes next in line. It draws a ball of radius R. There is no facility in there. It should be an outlier. I go on, I select no facility, I draw a ball of radius 2R. So in the end of this, at the end of this, I have a bunch of representatives. Every representative has some children that they're responsible for. And I have potentially one selected facility for every representative. So each representative looks at how many children they're responsible for. So that's the number, purple number that I've written. So that's the number of children that they're responsible for. And the algorithm is as follows. I want to open at most K facilities. So I look at the representatives in decreasing order of number of children, and I open the K largest. So in this, for example, if K is equal to 2 in this picture, I picked 5, so there are numbers of 5, 2, 2, 1. I picked 5 and 2. I open those orange facilities. And the people that I cover are basically the children of these representatives. So that's the algorithm. Okay, so a couple of things that, maybe a note for later future thing that is going to come up. I really did not use the X values at all. I only use the coverages, how much a client is an inlier or not. This will come up in a little bit. Okay, so about this algorithm itself, what is again clear that if I cover a client, I'm within distance 3R from an open sector. And this is, at most K centers are open is by design. So there's nothing really non-trivial to say, and that's why I strike it out. But what is not clear is why is 5 plus 2 at least M? Like why have I covered at least M clients? So I want to go down this a little bit. It's very, very elementary. Let's understand why this is true. That why does this algorithm cover at least M? And let's see what's going on. I know that the total coverage is at least M, because that's what the LP says. Total coverage is at least M. All the clients are partitioned into children. Okay, so I write this as I sum over all representatives, I sum over their children, and I take their values. That's just writing it differently. And now I'm going to use the greedy property that any child has its coverage at most its representatives coverage. So I can say that this is at most, so this sum here is at most the coverage of the representatives times the number of. Okay. Is that clear? Good. So again, coming back to this example, maybe where there were 4 representatives, I basically have the following constraint that whatever M was, I know that 5 times the coverage of representative A plus 2 times curve B plus 2 times curve P plus 1 times curve Q at least M. That is what I know from the LP itself. I open 5 plus 2. So why is that at least M? Well, now I'm going to use the fact that this curve A. So what is curve A plus curve B plus curve P plus curve Q? I want to argue that this is not too large. Why? Well, what is curve A? Curve A is at most the x mass of this ball here. Okay, that's the another constraint of the LP. Curve B is at most the x mass in the yellow ball around 2. Curve C is at most the yellow ball around P. Curve Q is at most around Q. So curve A plus curve B plus curve Q plus curve C. The total coverage of the representatives is at most the total x mass that is out there. What is the total x mass? Well, I've opened at most K facility. So this number is at most K. And so I have two constraints now. The second constraint says that sum of the curves is at most K. And the top one is a linear inequality, which is saying that that linear inequality is at least K. What is my algorithm? My algorithm is picking the K largest ones. So the K largest ones must be at least. That's my prediction. So that's the whole. So if I pick greedily, the sum of these coverages at least. So that gives a T approximation. Okay, so that was a different T approximation for the problem of K center, K supply with outliers. So I have been a lot of okay. Any questions? Good. Okay, so what happens with when I have weights now on sectors? Well, I can write the same LP. The difference, only difference for the natural LP is instead of number of open centers being at most K, I have the weighted sum of open centers being at most K. That's the natural LP I start with. And this is going to be bad. So let's look at the bad example. So here's a bad example. Again, hopefully I have not mucked up this one. So I have this is my metric space. I have two centers A and B, possible centers. And they have clients, 6 clients all around them, and across them they have distance infinity. So let me see if I have good. So the weight of A is 6, weight of B is 1, K is 6. I can open at most 6 things, but I have to cover 11 of these. So what is opt? So if I have a budget of 6, I really cannot do much, right? So if I have a if K is equal to 6, I can open at most one of them, and I cannot cover 11 clients with any finite orders. On the other hand, LP can cheat, and this is again similar to the minimum knapsack in the other direction. The LP can cheat by opening, the first client, the A client whose cost is high, up to only 5, 6. Those numbers are chosen for pathologically, but basically it's chosen so that the number of inliers, so every client here on the left thing will have coverage 5, 6 because this is 5, 6. And all the clients on the right thing will have coverage 1. So the sum of these things will be there. This is how it will be cheap. And okay, so before so it's worthwhile to sort of see why does the previous algorithm fail before looking at how to fix it. But maybe one point to mention is that it is a priori not clear how to add like knapsack covering constraint, because it's not a covering problem, it's a packing problem. And a priori it's not clear what constraints to add so that it will generically work. But I think I want to sort of go via, at least for this, why does the previous algorithm not work? So what is the previous algorithm? The previous algorithm will pick a client with the largest coverage. It will be from someone from the right. So let's say that client Q. And as soon as I draw a ball of radius 2R, all of these clients will be covered. And then I'll go to somebody on the left and I'll cover all of these clients. So my covering algorithm will end there. A and B would have been selected. And now I can still make that argument that we made, the sort of greedy argument, to say that this linear combination of these curves, which was this weight of number of children of P times curve P plus number of children of Q times curve P is at least 11. That is still okay. But what goes down the drain is that I don't have anymore. I cannot say curve P plus curve Q is at most 6 because the weight of this facility will come into play. And I have a different linear inequality saying that the curves are related by at most something. And there is simply for this set of equation, so this itself is a knapsack problem. So if I ask you, is there an integral curve P and curve Q that satisfy these two constraints? That is a knapsack problem. And just to make sure, can this knapsack problem be solved in polynomial time? So there is one class of knapsack problem that can be solved in polynomial time when the numbers are not too big. And what are these numbers? Well, what is the profit? The profit is number of children. Number of children can be no more than n. So this is a knapsack problem that can be solved in polynomial time and decided whether there is a solution or not. So if there was a solution, I would find it and I would get a nice algorithm. But sometimes, as is in this example, there are no 0-1 solutions. So how do you find inequalities to weed them out? So we can, in this example, stare at it and say, okay, so and so thing must be a valid inequality, and we can add it, the constraint that is satisfied with all 0-1 solutions, and then add it, we'll cut away, and I'll repeat it, and I'll find that the answer R was too small. The question is there a principled approach to get this? Okay, so that's what I want to spend the next 10 minutes maybe telling that, and then we will, I'm sure, open problem and I'll maybe conclude earlier. So maybe the bigger picture is any integral solution is actually a convex combinator of all integer solutions. That's the tightest, in some sense, tightest LP relaxation one can look at. And maybe one should just start looking at that. That's maybe the high level picture. So let me say what it is. So what is a set of all valid inequalities? So I just need the coverages of every client to run my algorithm, the LP guided output function algorithm. And I'm asking, what are the valid inequalities they satisfy? Well, this is probably the tightest one, right? So, okay, so this is, let me, so this is. So I want to say that the curve V's, any valid curve V's should be a convex combination of what coverages you can get from integer solutions. So for example, if you have this integer solution where I open that orange things are 1 and I have everything else 0, then the clients in blue that are visible to you have coverage of 1 and everyone has a coverage of 0. So if and this one, the previous one was a different set solution. So if you take the convex combination of this, you get this coverage is half on some, 1 on some, and 0 on some. More generally, any curve will look like a convex combination of such solutions. So you can write them down. You can actually write them down. It is basically, I have a variable for every feasible solution. What is a feasible solution? A feasible solution is a set of solutions whose weight is at most. I have a variable for every feasible solution. There are exponentially many. And I'm taking the convex combination of them. And the coverage of every point is basically I sum over all solutions which cover this point and I take up their problem. So this is an exponentially many variable, but this is basically the integer color. Now, if my R, if my guess is too small, then this set is empty. My R has been too small, man, this set is empty. So if a set of inequalities is empty, then its Farkas dual must be non-empty, right? So this is sort of the best LP relaxation. And the algorithm, the idea of round cut, to remind you, starting from this curves, I'm running this LP guided Higgs-Schmalz. I reach to a knapsack problem, which is polynomial time solvable because the numbers are not too large. If I solve them and I cover at least m clients, I'm done. Otherwise, I want to find a separating hyperplane. How will I get this separating hyperplane? That's what I want to say. So again, so coming back to this, so this is the set of the primal, which has exponentially many variables. But the dual, as in this is sort of, you can automatically, mechanically do this. If you write the dual for this, you'll get the following thing, that if that is empty, or rather if that is non-empty, then there is a lambda v's, some real numbers for every client, so that any subset which can be picked by the algorithm, whose total weight is at most k, but in general, if it lies in any feasible solution that you can pick, then if I look at the clients that can be covered by it, their lambda sums has to be less than. Okay. So if this is non-empty, then this lambda v will act as a certificate of the non-emptiness. Put differently, if in my rounding algorithm, if I fail to round, if I fail to find a knapsack solution whose value is at least m, I will still get a win if I can come up with the certificates to kill the problems. And these certificates always exist. If this was empty, then these lambda v's always exist. I just don't know how to find them. But the hope is, and this is a generic thing, not for just this problem, but for other plus other problems that can be solved, is you can use your inability to round or inability to prove that your rounding algorithm is good to come up with the certificate which weeds out this bad point. Now I want to sort of contrast this with usual ways of valid separating hyperplanes. We're taking the problem and a priori adding them for every problem. And this is more sort of instance by instance. I'll fail on this instance, and for this instance, these will be my lambdas. For a different instance, I'll have a different separating hyperplane. So that's the idea. So how does this work here? So here, so again, this is sort of saying again what I said. So if I cannot round, then I want to find these lambda v's. And I want to sort of say, how will I find these lambda v's? Let me go back to the bad example. So this was a sort of a bad example where I came up with an knapsack problem where I wanted to have, I had 6 cup p plus 6 cup q at least 11 and 6 cup p plus cup q at most 6 or something, and I just, there was no knapsack solution. Well, you can use the lambda v's. So it turns out for this particular problem, the lambda v's, which is equal to the size of the children, satisfies as a dual separating hyperplane. So if the resulting knapsack does not fail, we can find lambda v's using the size of children, and that is used to separate it at an instance by instance. Okay. So sort of to summarize the method, I have a rounding algorithm up front which uses very little information, just the coverage of the slides in this problem. I have a rounding algorithm, proposed rounding algorithm, and if it fails to give me what I want, in this case at least m outliers, well, I sort of believe that if my curve v's came from the correct polytope, I would have succeeded. So if this has failed, then this curve v's don't lie in my polytope, which means that there is this Farkas certificate that does not lie in the polytope. Let me use my inability to round to find this. So that's the sort of the higher level picture that worked for this problem. This is the same thing. So this was my student Mariam Nagamani around 5 years ago, and since then this idea has had success in other clustering problems. I should say that most of these problems are for the K-center objectives. It has not quite made forays into other objectives like K-median yet. But for example, for something again that Samir mentioned, so fairness, where you have constraint, not that this constraint is not covering out like at least m clients, but some sort of the clients that are grouped into various groups, and I want to cover at least some fraction of clients from every group. So it's a generalization in some sense of these outlier or inliers things. For that, this rounder cut method has had success. The other problem that Samir said about non-uniform K-center, again, it's actually one of the open problems I can say. Let me say it, I have some time. So the non-uniform K-center, so what is K-center? K-center is saying I have K balls of radius 1 that I want to place all over my metric space, but then I dilate them so that all the points are covered. I want to figure out the minimum dilation. Now imagine you had K1 balls of radius 1 and K2 balls of radius 3 and K5 balls, K3 balls of radius 7 and so on. So you have different kinds of balls. You want to place them and you want to find the minimum dilation so that I cover every point. That's the non-uniform K-center. It's open to have a constant factor for this, even when the number of different kinds of radii are 3. Sorry, that's not true. But different kinds of radii is 5. We proved in our paper that if the number of radii is growing with n, it's hopeless. You cannot get it. But the conjecture is, I don't know if it's a conjecture, but it's an open question whether if you have constantly many radii, can you get it. So in our paper, we do it for 2 kinds of radii, of which outlier version is a special case. Then with the paper with my student, again using rounder cut method, we could do 2 plus epsilon. 3 kinds of radii, but the third radii is radius 0. It was soon taken to 3 kind of radii by this paper of Ria, Rauter, Swenson and Schitt. And then I think Inamdar and Varadarajan last 2 years again did 4 kind of. So 5 or more is open. I don't recommend doing 5 and then 6. So hopefully some other, but underlying all of them, there is this round of pattern. The other thing is this continuous clustering. This paper by CKL, right? So Vincent, Karthik, and you, and this result, which I find it very interesting. It says I'm looking at K median in RD, and the metric is L infinity. Again, correct me if I'm mistaken. The metric is L infinity, and I want to solve K median on this. But the center can be anywhere. Center can be anywhere in RD. So this problem, the K median problem, the hardness is 2, even when K is 4. Again, if the center, if the thing was discrete, if the set of possible facilities were discrete, this is an obvious problem. You can get polynomial time just going over all possibilities. But if I can open the center anywhere, that's what I'm calling continuous clustering. Then you have to pay factor 2. And any alpha approximation of the discrete implies a 2 alpha for K median for the continuous, 4 alpha for K means. And so the question that we ask is this sort of 2 and 4 inherent, or can you come up with better algorithms? And so again, and the hard question here is, how do I write even an LP when the facilities can be anywhere? So we wrote an LP again, which was exponential size, but we use the round robin method to get some minor results. So we can do the continuous K means get a 32 approximation, which is better than the current 4 times alpha for K mean, which is 9x. So again, the round robin method was used there. So there are some recent work that has happened.
So hold on, so you said that even when K is 4, it's hard. So you cannot approximate the continuous space by some kind of discrete space in RD. Yeah.
The
Because
best,
if you could, then you would guess every subset of.
yeah, so this is the L infinity metric. So the metric is still L infinity, and the D is not small.
And
The D is as, so you can basically get any metric. So nevertheless, I like that. I think this question is very interesting. Okay, let me then end with the concrete open loop. Right. So the setting is going to be slightly different. So the problem is going to be fault tolerant K center. Okay, what is fault tolerant K center? Again, clients, facilities living in a metric space. I want to open. Okay, but every client now has a number. Okay, LB. Think of LB as 2, 3, 4 or something. Okay. It's fault tolerance. Output is, again, I want to open a center set S, but now a client is worried that LB minus 1 of these facilities will fail. So instead of looking at its closest facility, it's interested in its LV at closest facility. Okay, so the LV is 2, maybe for this client here, LV is 2. So it's interested in the facility that is not the closest but second closest. Okay. So let me call that DLV of V. So I open a set of facilities. Every client is looking at its LV at closest facility. Okay. And the problem is the same. I want to open K centers so to minimize the maximum a client pays, and a client pays not the closest facility, open facility, but the LV at closest. So that's one way of talking about fault tolerant case. The problem here? Again, there are various ways you can define fault, like why should I look at LVF? You can take an average of all the, but let's just stick with this notion. So it's not too hard, again, when we should teach Hogbaum Schmoes and then want to give an exercise to say design a 3 approximation for this. So this problem, there is a 3 approximation. But then you can ask the outlier. Now I have outliers, what can I do? And so again, this is the setting. I have m clients I need to cover. I want to minimize the max only over the inliers. The answer is I. What we could do is get a 4t minus 1, not 40 minus 1, 4t minus 1 approximation, where t is the number of different LVs. So this problem, this sort of fault tolerance, people look at the uniform version or all the LVs are same, 1 or all the LVs are 2 or all the LVs are 17. For that, we get a 3 approximation. So when t is equal to 1, we get a 3 approximation. That's good. But t can be as big as k. So we really don't get a great approximation. So this is also, and to get this 4t minus 1, we have to throw in the same hammer, the same method of, you look at you have an algorithm, and if it fails, then I have separating hyperplane. So it's the same setting. So we don't know what the answer is for this. Then the problem might seem a little, contrived and artificial. I think at some level it is. But here is the bigger meta question, and maybe some of you know the answer. I don't know of a clustering problem where the outlier version is probably harder than the vanilla version. And maybe it's because we don't have very good tools to prove hardness, but again, I'm not an expert. But here is a meta question. Come up with a clustering problem, which is, let's begin with even a pathological clustering problem. Then we look at natural ones. But maybe this is a concrete example, the fault tolerant version, where the vanilla version without outliers has a constant factor, but the non-vanilla does not. It's super constant. I don't know. That's one maybe. So the concrete question is to see 4t minus 1 is correct. The less concrete is there a different problem so that there is separation? And more generally, can the round or cut method be used for other objectives like k-median? Yeah.
So the median case center is the same thing.
I know, but it's how much is the gap?
1 plus square root 3 you can do.
Yes.
So outlier you can push it to 3.
Yes. So I want so that it's important that I'm saying constant and super constant. There is another problem I know where there's a gap of 2 and 3, but I want a little more. Is there a bigger qualitative difference? I think the answer should be yes, but we just don't know.
We generally tend to super constant lower bounds.
So I think maybe that's the reason. Maybe the reason is that we just don't have the tools to do super constant lower bounds. So maybe then the fault tolerant robust version is a concrete example. I don't know. We tried for a while to beat. This seems to be the limit of our knowledge, or come up with a constant approximation for this, which will not answer this question, but some. So the other thing is whether this round or cut method actually has powers to do other objectives like k-median. K-median with outliers is another problem where we have algorithms by iterated rounding. So anyway, that's more meta. So I will sort of end it. Thank you.
Are there any additional questions for Deeparnab? So I have a quick question. So for cut and round, like when I have a separating, is it clear that I only need polynomial?
Yeah, so there is some work needs to do to the polynomial that you have, it should be able to be cut in a ball of radius r and small r. So those are usually easy to check. Nice. As you know which kind of inequality you add them up for check. That technicality is there, but modulo that is correct.
Additional questions?
So there has been no use of Euclidean metric quality in this cut and round.
There actually has, I think, Eun and so the Euclidean K supply problem with outliers was also looked at by Eun. It's the same, I think, Vishwanath, Eun, and forgetting the third of them, but they use the round or cut method. Yeah, basically, the set on which you want to run edge cover on is not clear, right? So that's what they say. Just add all the constraints and figure it out later while rounding.
I see. In the matching day.
Okay, if there is no additional question, let's end it now.